I'm asking this because we're comparing two methods, PLS regression and PLSCanonical, both used in multivariate regression, which is predicting multiple variables at once. I noticed a big difference in how they explain the variance, which means how much of the variation in the data they can account for. I want to understand why this happens. Let's dive into the details. PLS regression is a method that focuses on maximizing the covariance between the predictor, X, and response, Y, variables. Covariance measures how much two variables change together. In simpler terms, it's like looking at how closely their movements are linked. This method is less sensitive to how the individual variables are scaled, meaning if they are large or small numbers. PLSCanonical, on the other hand, aims to maximize the correlation between the latent variables derived from X and Y. Correlation is also about how much variables change together. But unlike covariance, it only considers the direction, positive or negative relationship, and not the magnitude. It's more affected by scaling of variables in X and Y. This describes the core principle of PLS regression. I'm focusing on maximizing the covariance, which is a measure of how much variables change together. Remember, this is less sensitive to changes in how variables are scaled. That means I can change the size of the numbers and the covariance will not change as much. This explains PLSCanonical's approach. I'm maximizing the correlation, which shows the relationship between variables. Unlike covariance, it's more concerned with whether they move in the same or opposite directions. Crucially, correlation is highly sensitive to variable scaling. I'm keenly affected by the size of the numbers. Here, I'm highlighting how scaling, changing the size of the numbers in datasets X and Y, affects the results. PLSCanonical is greatly affected by this. However, PLS regression, less so. This points out that PLSCanonical does something specific to datasets X and Y before analyzing them. It is called standardization. It makes them all have the same average and spread of numbers. This has a big impact on how the results turn out, unlike PLS regression. Here, I directly compare the main differences between the two methods. PLS regression focuses on covariance, which measures how much X and Y variables move together, while PLSCanonical works with correlation, which measures the direction of that movement. I see this as the core question. We're comparing two statistical methods, PLS regression and PLSCanonical, and investigating why they give different results for explained variance. Explained variance refers to how much of the variation in the response data, Y, can be explained by the predictor data, X. The core difference lies in how each method handles data scaling and its optimization goal. This statement highlights a key difference. PLSCanonical is very sensitive to how the data is scaled, the size of the numbers, because it focuses on correlation, which is affected by the magnitude of the variables. PLS regression, which focuses on covariance, isn't as impacted by scaling. Think of it like this. Correlation measures the direction of the relationship between variables, while covariance looks at both the direction and the strength. Scaling affects the strength aspect more. This explains why scaling affects PLSCanonical. PLSCanonical does a pre-processing step where it standardizes X and Y separately. Standardization ensures that each variable has a mean of 0 and a standard deviation of 1. This step directly impacts the correlation calculations that PLSCanonical uses. PLS regression doesn't do this separate standardization, so it's less affected by scaling differences. This statement gets to the heart of it all: the different optimization goals. PLS regression aims to maximize covariance, a measure of the linear relationship between variables considering both direction and strength, while PLSCanonical aims to maximize correlation, a measure of the linear relationship considering only direction. These different objectives lead to the differences in sensitivity to scaling and ultimately to the different explained variance ratios. I see you're curious about why the explained variance differs between these two algorithms. That's a great question because it points to the core difference in how they work. The explained variance tells us how much variation in the data is explained by the model, and the difference comes down to how each algorithm handles the data and what they try to maximize. PLS regression, as you'll see below, focuses on overall covariance, while PLSCanonical cares about correlation between the components they generate. That makes a big difference. PLSCanonical is really sensitive to how your data is scaled because it works with correlations. Remember, correlation is about the relationship between variables, and that relationship can change dramatically if some variables have much larger values than others. PLS regression, however, is more concerned with overall covariance, which is less sensitive to these scaling changes. Imagine it like this. Covariance is about the overall spread and direction of data points, while correlation is about the tightness of the relationship. Scaling changes the tightness but not necessarily the spread. Here's the key. PLSCanonical does an extra step. Before it even starts its calculations, it standardizes, or scales, both datasets, X, predictors, and Y, responses, individually. This standardization centers each variable at 0 and scales it to have a standard deviation of 1. Because of this, any differences in the scale of your initial X and Y data are removed, so you're working with equally weighted variables. That's not the case with PLS regression, and that difference causes those distinct explained variance ratios. This pre-processing step in PLSCanonical is a critical difference that affects the final results. Let's break down PLS, partial least squares, algorithms. PLS regression aims to maximize the covariance between your predictor variables, X, and response variables, Y. Covariance measures how much two variables change together. PLSCanonical, on the other hand, wants to maximize the correlation between the latent variables it creates from X and Y. A latent variable is a hidden variable inferred from observed variables. Correlation, unlike covariance, measures the strength and asterisk direction of the linear relationship between variables, and is highly impacted by the scale of the data. That is the primary difference leading to different explained variance ratios. While it's true that the number of components you choose impacts the explained variance for both PLS regression and PLSCanonical, it doesn't explain why they show such different explained variance ratios. The key difference remains the scaling issue and how they handle it. I see the core issue here as understanding why the explained variance differs between PLS regression and PLSCanonical. It's all about how each method handles data and what it's trying to optimize. We'll explore these differences to understand the variations in explained variance. This sets up the scenario. You're using two different partial least squares, PLS, methods and noticing different results. We need to pinpoint why the explained variance, how much variation in your data is explained by the model, differs. This is a key difference. PLS regression focuses on the overall relationship, covariance, between your predictor and response variables. PLSCanonical, on the other hand, dives into the relationship, correlation, between the underlying components, latent variables, derived from those predictors and responses. This highlights the impact of scaling, adjusting the range of your data. PLSCanonical is very sensitive to it because correlation is affected by the magnitude of variables. PLS regression is more robust. This is a crucial detail. PLSCanonical pre-processes the data by standardizing the X and Y datasets individually. This standardization changes the scale of the data, which affects correlation calculations and therefore the explained variance. While the number of components used definitely impacts explained variance in both methods, it's not the primary reason for the asterisk difference between them. This describes the core function of PLS regression. It aims to maximize the covariance, which measures the overall linear relationship between the predictors, X, and the responses, Y. This means changes in the scaling of X and Y won't significantly change the results of the PLS regression. This is the aim of PLSCanonical, to maximize the correlation between the latent variables derived from X and Y. Unlike PLS regression, the scaling of the X and Y data significantly affects the outcome of PLSCanonical. This step is unique to PLSCanonical. Before analysis, it standardizes the X and Y datasets separately. This is a crucial step that leads to differences in explained variance compared to PLS regression. This question asks you to identify the reasons why the amounts of variance explained by the different components differ between these two similar-sounding methods. I'll help you to understand the subtle but crucial differences. PLSCanonical is very sensitive to how the data is scaled, the size of the numbers. If you change the scale, you significantly change the results. PLS regression isn't as sensitive to this. Imagine comparing heights, in centimeters and meters. The correlation would be the same, but the covariance would change. That's because PLSCanonical is all about correlation, while PLS regression cares about covariance. PLSCanonical preprocesses the data by standardizing each dataset individually before calculations. This standardization changes the scales of each variable to a common reference point, mean of 0 and standard deviation of 1. This separate scaling isn't done in PLS regression, which explains the differing explained variances between the two methods. This statement highlights the core difference. PLS regression tries to find components that maximize the covariance, a measure of how much two variables change together. PLSCanonical aims for maximum correlation, a measure of how strongly two variables are related, regardless of their scales. Think of it like this: covariance cares about the magnitude of change, while correlation just cares about the direction. While increasing the number of components in both methods affects how much variance is explained, it doesn't explain the difference observed between them. The difference in how they are sensitive to scaling is far more important in explaining the difference in explained variance ratio between them. This question asks you to identify the reasons why the amount of variance explained by the different components differs between these two statistical methods. We're looking for the underlying reasons, not just the surface-level observation. I'll explain this one first because it's pretty straightforward. PLSCanonical is very sensitive to the scales of the input data, x and y, because it focuses on correlation, which is affected by the magnitude of the numbers. Think of it like this: if you measure height in centimeters versus meters, the correlation might change quite a bit. PLS regression, on the other hand, uses covariance, which is less affected by scaling. It's like comparing apples and oranges. One is more scale-dependent than the other. This is a direct consequence of the previous point. Because PLSCanonical is so sensitive to the scaling of the data, it needs to standardize, or normalize, the x and y datasets individually. This preprocessing step is exactly what causes the difference in the explained variance ratios compared to PLS regression, which does not require this extra step. It's like baking a cake. You'll get very different results if you use different measuring units or don't follow the recipe correctly. This statement gets to the heart of the matter. PLS regression aims to find the components that maximize the covariance, a measure of how much two variables change together, between the predictor variables, x, and the response variables, y. PLSCanonical, however, goes a step further and tries to maximize the correlation, a measure of the linear relationship between two variables, between the latent variables derived from x and y. This difference in objective is what drives the distinction in their behavior concerning data scaling. This statement is incorrect. While it's true that the number of components used in both methods affects the explained variance, the key difference lies in how sensitive they are to scaling, not simply the number of components used. It's about the underlying mechanisms, not just the superficial adjustments.